All right. So I'm going to now leave the floor to my colleague, Ilyas, who's going to open the discussion on the generative AIs and in O-RAN stack. So please, Ilyas, start sharing your screen. I'll mute myself.
Okay, hello everyone. I'm Elias. I'm a PhD at Eurocom here. So you can see my screen, right? Okay. So far we explored more or less the rig part of the O-RAN architecture. So we will try now to expand and see how OpenRAN Studio can implement the full O-RAN stack. And we will try to go a bit forward looking to see novel use cases for 6G, for example, generative AI and large language models, and in general, how the platform could be used for AI. So in this figure, maybe I'll close this. So in this figure, you can see at the left part, you can see we have for reference the full O-RAN stack. We have the SMO, near real-time rig, the non-real-time rig, and all the interfaces. And from the right part of the figure, we can see the OpenRAN Studio full implementation of the O-RAN stack. So far we focused on the bottom part that we saw the 5G cloud native version of the core, the CU, the DU, the UE, for example. We saw the FlexRig, the near real-time rig, and the xApps with the E42 and T2 interfaces. So now if we go a bit higher, we can see that we also have custom implementations of the SMO and two important components inside. One of them is Athena, and the other one is Odin. So Athena is more for the management and fault tolerance part, while Odin is more for the non-real-time rig implementation for RAN optimization of the RAN, yeah, for policy enforcement, for example. And on the southbound, we can see that we have the A1 and O1 interfaces. And from the northbound, we can see the R1 interface with the RAPs. So these RAPs can consume R1 services both from Odin and from Athena, so they can manage, control, and in general operate the 5G network in real time. So in order to explore, for example, GenAI and large language models, we will present two demos. The first one will be on throughput SLA negotiations. So we will create some GenAI agents that will try to negotiate on the throughput SLA. And afterwards, they will try to optimize the RAN using the RC service model. And we will also show a second demo, which will utilize the RC and with CCC service models that we already showed, and it will be for mobility and spectrum management. So this is the first demo. So as we said, we have the full O-RAN stack, right? So here we have the SMO, the non-real-time rig, the near real-time rig, and we have a base station, let's say, and the UE is connected already. So here we are talking about an intent-based network implementation. So the communication between the agents that we will discuss and also the communication between the various components is done by means of an intent. And we have the multi-level O-RAN APIs, as we said, and this network, we can assume that it is shared between multiple business parties, for example, MNOs, MVNOs, vertical service, etc. Okay, and we try to show that how in this demo how you can implement multi-agent systems with different agents that have different roles using GenAI and large language models. Okay, so here if we start from the top, we see that we have LLM agents that their main role is business negotiation. So they negotiate on the throughput, and after they decide which value, because they share the same network, they need to decide and agree on the same value, for example. Maybe they have conflicts and different roles. So if they agree, when they agree, they send this as an intent to another agent, which is here, the executive LLM agent. And this one now has the responsibility to control and manage the network in a closed loop manner in order to enforce this intent and actually see the desired throughput on the network. So let's move to the demo very quickly. So here, if I go, okay, then. So if I go back to the beginning, you can see that here on the upper left part, we have the one UE connected. You can see that here it is around 20 megabps, let's say, right now. And on the bottom part, we see the logs of the non-real-time rig that will receive the policies. Here we have the CLI that we can see all of the pods that in the full network, the core, the RAN, and also the UEs connected and the xApps. You can also see the vendors, correct? You can see which vendor is which pod, for example, the status of the pod, if it is ready or not ready yet, and along with other statistics. Here we have, for example, you can also see specifically the terminal, specifically the runs, Springfield run is deployed, what xApps we have. Here we have 3 xApps, for example, flex policy, flexmon, and monitoring. I stop here. I just want to show that the flex policy, for example, if you see it is written in Go and it doesn't use a database, and the service models that are used are max license RC, for example. The flexmon is more for monitoring, dynamic monitoring. It's written in Python, timescale DB. So you can have detailed descriptions of each xApp. Okay, and if I move now, you see that we have 20 megabps of traffic. Maybe I put a bit. Okay, I can speed up. So now, just to remind you that first we have the business LLMs that will try to negotiate on the resources for the throughput. So here we use 2 agents. We give them names. For example, this one is Ali. We give this name, and you can choose the personality of the agent. So if for example, you can have different agents. For example, they can be vulnerable, they can be agreeable, they can be disagreeable, normal. This just changes the description of the agent and the role. So let's say that we have normal and not malicious agents. So they will start negotiating. Here, I just want to mention that they have different objectives. Okay, I will also show okay, so now we see both agents, their first message. So they have different objectives. The first one, Elias, wants to reduce the cost. So it wants to minimize the throughput, while the other wants to enhance the performance. So it wants to maximize the throughput. So they talk like humans, more or less, and they have used also a template just to talk about the parameters that they want to control. Here, the parameter is throughput. And if we let them discuss, first one proposes 5 megabps, the other proposes 20 megabps. They try to come to a consensus in the middle, let's say. So after some time, they reach to a consensus, let's say to an agreement or disagreement. If they agree or disagree, if they disagree, for example, the network is responsible, but here they agree. The agreement was 15 megabps, as you can see. So this now goes to another agent. Its role is to control through the O-RAN APIs of the platform. So here we can see that we have, on the upper right part, we have the LLM agent that try to control. And on the lower part, we have the O-RAN. So here the LLM sends the policy. First, it was 50 PRB resources, then it was 40 PRB resources. And we can see that also it goes to the non-real-time rig here. So this is enforced to the network. And you can actually in real time see also that from the UE perspective, the throughput is changing. So here, in only 2 inferences, the throughput converts to the desired value with a 5 megabps tolerance. We also support the dashboard that you can see it also here, along with other metrics. And that was this demo for the collaborative LLMs on top of the OpenAirInterface Studio platform. So I want to continue quickly to not waste any time. So the second demo with LLM and GenAI is for mobility and spectrum management. So here, again, we can assume that you can have LLMs that they negotiate for spectrum sharing, let's say. So they will negotiate on, for example, spectrum sharing in FR3, for example, there are, or CBRS, there are the primary user And the secondary users, they can negotiate for the spectrum offers, what spectrum should be available at what cost, for example, prices. And in real time or non-real time or very like short-term intervals or long-term, it depends on the use case, they can send different offers. So here we assume that first the LLM negotiate, and in a second time, then the LLM sees the available offers, and based on its objective and its role, will pick the right one. So here in this demo, the main objective of the LLM is the cost optimization. And this means that it receives the cost intent and it wants to match or come as close as possible to this intent. So based on the available offers, it will try to find the appropriate intent and then reconfigure the base station. So here, if we need to change the band, for example, to another band, or if we need to change the bandwidth of the same band that we need to reconfigure the base station, we will hand over all the UEs to a neighboring G0 B in a fourth step. So we hand over all the UEs to the neighbor's G0 B. We reconfigure the G0 B that we want to the appropriate band, and then we bring them back, all the UEs. So we have in real time, without like UE disconnection, we have the reconfiguration of the cell to the appropriate band. So let's go to this demo. So here at the beginning, so we use the Amarisoft run. So here in the beginning, we can see at the bottom that we have, let me see the quality. So maybe it's more clear now. We can see that we have an N78 band with 20 megahertz of bandwidth. And now new offers will come, spectrum offers will come. So if yes, this is it, N78. So here we start the proxy agent and we start also the RAN part and the near real-time rig. So if I stop here, let's say that this is the first slot that an offer is coming. Actually, there is the negotiation that already happened, and here we have the available offers. So the large language model will receive the agent, will receive the available offers. Here we see that we have 3 spectrum offers available. 2 of them are in 78 band and 1 of them is in 41 band. And all of them, they have 20 megahertz bandwidth, but they have different prices, as you can see, 200, 300, and 100. So if we see first that the network cost intent here is 100 euro, this means that the LLM main objective is to try to either match it exactly or bring it as much as close as possible to 100 euro. Here we see that there is an offer actually at 100 euros. So we want to see that the LLM will choose this one because the current offer is the N78 with 400 euros per hour. So it was quick, but the LLM action offer index is 2. So in 1 second of inference time. So the chosen offer is the band 41 with a cost of 100 euros per hour. So immediately after this one, an algorithm understands that the xApps will understand that to adjust the network you need to adjust the network to a different band. It's a different band, it's not the same one. So the handover will run. Here the xApps runs the handover, runs the CCC, the reconfiguration of the cell. Successfully, handover successful. So we did the handover and we came back. This is another slot, let's say the second slot with other offers with different prices. And we can see that, for example, we don't need to change the offer right now. So if we check the base station now, based on the first slot and just to see if the base station is reconfigured. If I move a bit faster here, we can see that, yes, actually the band right now is the 41 with 20 megahertz of bandwidth and the different RFCN. So the cell is reconfigured in real time. Without, and on the right part, you can see that the pink is still running, right? Okay, so this was also the second demo. So if we want to have some takeaway messages here, is that through OpenRAN Studio, with these basic building blocks that we described, we have the service models, the KPM, the O-RAN service models, the RC, CCC. We have this O-RAN stack with the RIC, with the SMOs and all the interfaces. And we can realize and experiment and educate also on the 6G use cases, for example. We can try to imagine and experiment to see what is the future, right? So we can test some KPIs. Here, some of the KPIs that we saw was spectrum agility on different offers. So you can be agile and flexible on your base station configuration in real time, and you can adjust it without losing the connection in the orders of seconds. And another one was how fast was the inference speed of the LLM. It was below and around 1 second. And how fast the LLM could converge to the throughput intent, for example, it was around 2 or 3 iterations. So also the use case, let's say, that we saw was FR3, spectrum management use cases, or spectrum sharing, CBRS use case, and LLM assisting 6G RAN slicing. So without further ado, this was the GenAI demos, let's say. I will now, yes, I will now give the floor to Mikel again. So I will stop sharing my screen. So please, Mikel.
Hi, thank you. Thank you very much for the demo. Let me see if I can share my screen. So let me try it again. Can you see it now?
Yes, Mikel, your screen is working. Please go.
Thank you very much. So let's talk a bit about the O-RAN and 6G. So towards 6G, so 6G is beyond just connectivity, right? I think that we all know this, and it has different dimensions here. We want to talk about some of them. There may be something more, but it's definitely a fusion between the physical and the digital world. Yes, we are talking here about digital twins. There will be emerging applications and services, right? Collaborative communication and computing, right? Intelligent digital twinning, the metaverse, extended reality. These are definitely things that they will play their role in the following years. And regarding all these kind of applications, that generative AI, it will be at the center, because if we can prove that it's an intelligent, it can intelligently optimize things or simplify and control and management, it will definitely be a revolution in this regard, right? GenAI is also about abstraction of the objectives that we may have, right? Let's go also about thinking a bit outside the box on the road to 6G. So we see two directions in BubbleRAN right now. The quality of service, and so the buffer load in 5G, and for that we developed the traffic control service model, where you can also control the application level quality of service. For this, we will give now a demo, and we also see some ISAC, right, and 3D mapping with sensing, localization, and positioning. That's something that it will play its role. So regarding the buffer load in 5G, latency is perceived at the application. This is very basic, but sometimes forgotten, right? We can say, you know, like my latency between these two endpoints is milliseconds, right? But then my application is not working. So what's going on, right? And we, in contemporary this actually the slowest data link in all the path is the GNOD, right? Is the air, right? I mean, you cannot compare the speed of the air with the speeds that we can have on fiber. And thus, we suffer this buffer bloat phenomenon. Here we tried with 2 runs, with Amarisoft and OpenAirInterface, a 5G SA. We ran a program basically from the buffer bloat .com a web page actually that they provide, where they basically try to saturate the links and measure which is the effect of these buffer bloats. So they basically send you 4 TCP flows, 3 UDP flows, and 1 ping, and they measure, right? So here we can see that on the upper part, the throughput is around 150 megabps for Amarisoft and for NoAI. The aggregated one, we can see that every 10 seconds, actually, there is a spike down. This is due to the congestion control algorithm. It's about BBR, right? You can check it, but the idea of this congestion control algorithm is that every 10 seconds, they want to infer the bandwidth. So they basically stop sending data and try to measure the available capacity for them. Anyway, like in these 2 networks, we have delays that they are beyond 100 milliseconds, which it may be more than what it is permitted for many applications. In fact, in 5G, they knew this, and they came with something that it's called low latency, low loss, and scalable throughput, or L4S. You may have heard about it. In the release 18, actually, they added, the basic idea is that when you detect that there is, this is the RLC, on the RLC buffer, a lot of packets they are accumulating, you inform basically PDCP to mark the packets, the explicit congestion notification bit, so that the sender, when the packets comes back through the ACK, it knows that there is congestion, and basically it will stop transmitting packets. This is taken directly from 3GPP to enable ECN marking for L4S in NG-RAN. Dedicated quality of service flows are used for carrying L4S-enabled IP traffic, yes. And the criteria based on which NG-RAN decides to mark ECN bits for L4S is NG-RAN implementation specific, right? So they are basically saying you can mark the packets maybe if you have, depending on the amount. So if a lot of packets they accumulate there, you may want to mark them. Or you can use something like CODEL, control delay. It's not about the number, it's about the sojourn time. So if the packets actually they arrive at the RLC buffer and they stay there for, I don't know, normally what you do is you put a window, right? And a time. So for instance, in 100 milliseconds, all the packets, they were suffering more than 5 milliseconds of delay, you mark it, right? And you do it on PDCP because after PDCP, it's not an IP packet anymore, right? PDCP, it's about integrity, ciphering. I think that you probably already know like the players in 5G. So which is the BubbleRAN's approach to this? So we develop a service model. This is called traffic control with 6 stages. Basically, a polisher, a classifier, a queue scheduler, and a shaper, right? You can see it here down. The basic idea is that, well, first the packets on downlink, they will come from the SDAP to our TC run function, because this is basically embedded on the run. So we'll get it into our classifier. The classifier will say which kind of packet we have, right? Then it will go through a polisher. The polisher will say like, okay, you can go to the queue. You maybe redirect it to another queue, maybe because you have gone beyond the available bandwidth, or maybe just drop the packet. The third stage is a queue. We can think of CODEL, a FIFO queue, explicit congestion notification. So we may mark the packet if we want to. We may, with CODEL, just throw the packet, right? Then we have a packet scheduler, because we may have as many queues as we want. Then we have a shaper. The shaper is per queue, so we can manage and shape actually how much data we have. So the classifier can say like this flow come to this queue, and then through the shaper we can say like, and this is the maximum bandwidth that we will give to this specific flow. And the last stage is a pacer. The idea of the pacer is basically to not overload the RLC buffer. So it will just send packets, keep the pipe full but not fuller, like the famous paper of Leonard Kleinrock suggests in his title, right? So we want to send packets, but we don't want to create here a deep buffer full of packets that it creates a delay. TC basically is a superset of L4S. In fact, if you go and read the paper that we presented on JSAC, we do some experiments regarding L4S. So we also applied this explicit congestion notification. Of course, you need a TCP PRAC for that. I mean, you need a special congestion control algorithm that it does understand these bits. But you can use it right now straight away in our stack. You can also go to the second link. A second link is they did us an interview on the JSAC blog regarding what we were presenting and which were our ideas, right? So after this paper, so what we did is we had a classifier with a deep packet inspector. So this means that we are capable of segregating more than 100 flows. I'm talking about YouTube, Twitch, Spotify, Zoom, Ads Analytics, Google Hangout. I mean, we can really understand what kind of packets they are going through the stack. And I'm going to throw here a challenge that I haven't seen it resolve, and probably machine learning or artificial intelligence may help here, which is definitely challenging. So we need to model the application behaviors, right, and provide some kind of control loops to optimize the traffic. Now, the problem is that YouTube nowadays does have more than 30 flows. You may have TCP with different congestion control algorithms, right? Because sometimes when you start YouTube is with PBR, but sometimes it's with cubic. UDP traffic, quick. So sometimes we have UDP, but also we have some kind of intelligence afterwards. We may have a DNS. Data packets may arrive, and they do arrive in batches, right? So it's not that we have like a UDP constant arrival of packets. So it's not that easy to monitor in that way. And that data path, in the data path, the bandwidth and the latency, it can also change, right? Because due to the modulation encoding scheme, for instance, the bandwidth, it does change. It's not that we have a stable bandwidth, right? In cellular networks, this idea is, they don't have this problem actually in wired networks. We do have this problem in wireless networks. And so is the latency also, since we also may have some harks, or they may accumulate beforehand. But additionally, the problem is that now there are many control algorithms together. So we have the one in the app in itself, and on top of that, we have ourselves, right? That we are controlling the RAN through TC, because through TC you can really segregate and have a very fine-grained definition of what you want to do specifically with which packet. So you have TCP on one side, you have TC, and then on the other side you have the application in itself, right? So the application may also want to optimize itself. For instance, in YouTube, it can be easily seen with the number of frames that you see, the quality that you have, right? I mean, you may have the quality if you put it on auto, if you have a bad bandwidth or a weak bandwidth, actually it will go down. We will see it right now. So let me show you a live demo, which I think that it's very, very interesting regarding this. In Nympho, we have a core network. On Atom, we will have the GNOD, the near real-time rig, and the xApp on TC. And then we will have a Pixel 5. So if we come here, so let me first start the core network. Okay, let's run here G0B. Okay, so everything looks fine. Let's try to connect. So very nice, we are connected now, right? Now, let's go to YouTube, for instance. So this is an application of a static noise for smartphones, for sleeping, studying. So it lasts 8 hours. So we will not be here. Oh, look, we even have ads. Let me see if we can run it. Okay, so here we are running it, right? Now, what we can do actually is we can come here. We are on auto, right? Let's go to stats for nerds. And here we can see like YouTube, how it is inferring the network status. This is very, very cool actually, because you see how they are trying to control it from their part also. So we are basically at 2560 times 1440, like in the resolution. Well, it could be a bit better at 30 frames, right? So this value is interesting, but also the other interesting values are here, the connecting speed, right? We are trying to infer which is the speed of our network, right? And we are trying to infer it so we can know actually which is our optimal resolution. Below you can see the network activity, right? So you can see when some packets are arriving. And below it, you can see actually the buffer health. So actually, if we stop right now the base station, we will still have like 15 seconds more or less, yes, of time where we can still watch our videos. Now, what happens actually if we run hyper and we bloat, what it will happen here on the application, right, is that the connection speed, it goes down, right? The application is seeing that actually it's going worse and worse, right? And actually the buffer is going also down, right? So we are losing our buffer time, and we are also inferring that the connection is worse, right? We can even see at some point, I don't know if we will see it now because we don't know how this algorithm works, at least up to the date, we may know it at some point, like the resolution going down, right? So, and if we stop it, of course, the buffer health will go up, and the connection speed, we will see it also going up, right? So the YouTube is inferring that it has a better one, right? Here we have seen also how the resolution, it went down before. If we now wait a bit, the optimal resolution, it will go up, right? The current resolution, because we are inferring that we do have bandwidth, right? So now the idea that we can have here is actually we can have a rig, right? And we can run this, right? But when we infer and when we know actually that it is not working as it should, or we see that the buffer is going down, or we just want to reserve some bandwidth for the YouTube traffic, what we can do is we can run an xApp. An xApp actually, that what it will do, this xApp will reserve some bandwidth for YouTube, right? So we will segregate this traffic and then give assign this bandwidth to it. So now, right now, they think that we have like 20 megabits per second, right? If we actually run it, it should go up, the connection speed actually from the application. So now it's 16, 17, you see, nearly 18, 27, right? And still it is running here. The flow is running, but we basically segregated here. We segregated the flows, So this is one of the things where we think actually that 6 is going to be about, or it could be about, right? About inferring these things. We also have here the video if somebody wants. The other topic that we believe is going to be important in the future is about sensing, location and positioning, right? So we are introducing now a new custom service model for supporting 6G ISAC, the use case. The service model, the data model, the idea is that we will have different IQ samples plus a couple of other parameters. We will try to passively sense and construct the physical environment. We will try with different cells, multiple antennas, different RADs, and also different technologies in the sense that we will want to mix Wi-Fi, 5G, maybe millimeter waves. There are some examples that we can go through them, relative positioning of spectrum energy. We can see the flare. We can actually have some interference detection, right? So background, the spikes and so on. We can also create heat maps and 3D maps. And it's a very inexpensive way of having a camera, right? Or kind of camera, because you can actually sense the environment around you. The trajectory tracking, of course, collision avoidance. I mean, there are many applications. We can also think that once that we create this environment, actually, for sending a message to a car for a braking or something, it's going to be really, really fast in the sense that we measure, we get this information, and we do it. We don't really need to go through to upper layers, right? And analyze the images there, like within a camera. However, like this demand for low latency, it comes with a huge amount of data, right? So we will need to see how we manage this. It's still doable, but it's also challenging. FlexRig is therefore like our foo on this. Sorry, it's not our foo, it's our friend. So we will see how it goes on the following weeks, but we will definitely have something. And example use cases, they can be like goal-oriented intelligent connectivity, right? So where do we want to have different goals? Digital twinning, I mean, this is also a very interesting thing that we will come in the future, probably with something. 3D network or crowd maps. And here, for the promotion and closing the session, I think that I will give the floor to my colleague, Ali Reza. Thank you very much.
Well, thanks, Mikel, for the long presentation. We have been 3 minutes, 4 minutes overdue already. So I wouldn't take much time. I just want to close the session, and then we could have a QA session for around 5 minutes after, 5-10 minutes after. Of course, you are welcome to send us your questions if you have any with our email on LinkedIn and other connection channels that we have. And you're free also to leave if you want. These videos are recorded and it would be published on BubbleRAN's YouTube channel in the following week. So I want to just close the session by mentioning how this whole ecosystem is merged into BubbleRAN's ecosystem. One is that, first of all, this OpenRAN mini-series is actually our forum to share our knowledge and foster academy-industry collaboration. We value your feedback a lot to improve the quality and format and the contents of upcoming series. We have a lot of other topics to discuss and share with you. To this end, also, OpenRAN Studio platform is designed with the following objectives: to empower communities and organizations, to accelerate the adoption of modern technologies, having a solid ground for tutoring the next generation of researchers and engineers, having reproducible and verifiable and consistent outcomes for the teaching and research, affordable and accessible means for education and research, and finally, opening new possibilities and dimensions via multidisciplinary research. I also would like to mention that we are soon going to have a new release in Autumn that would contain most of these features that we discussed in this presentation officially, plus some access to the source code for the SDK, which would be packaged separately for you to develop your own xApps, service models, etc. And in the meanwhile, for all of these discussions, you could continue checking out BR Flexic branch on the open source Flexic repository that contains our regular contributions to open source as well. We are going to have officially early support for 7.2 via Lighton and an OpenAirInterface included in this new release, as well as the official O1 support for Lighton all-in-one and ORU products. I would also like to mention the projects that are ongoing with BubbleRAN, which some of them are mentioned directly on the website, on the presentation. Some of them are mentioned implicitly. In particular, the 6G census project has been an active funding source for our ISAC activities, which are ongoing on BubbleRAN and are going to be added to the products and to this OpenRAN Studio as well. On the other hand, we have our activities on the 6G Cloud project, which involves improving the RAN architecture towards 6G and having more cloud-native RAN. We leverages FlexRig architecture towards achieving a more flexible control fabric on top of the RAN. And finally, the 5G Tactics project that improves our understanding of security in O-RAN and trying to address the different issues of security in the context of O-RAN. And finally, I would like also to mention that these projects are partially funded by EU Commission and 6G SNS, and to thank them as well to provide the fundings for those projects. Now we are at the QA session. I mentioned there's the link for our LinkedIn account. You could check with BubbleRAN. There's our YouTube channel at youtube.com/@BubbleRAN, and you could also email us at contact@bubbleran.com. Some details of the open ORS product you could check at bubbleran.com/products/mxors. And then we leave you the floor for a few minutes of the questions that you could ask directly from our people. Please turn on your mic and camera while you're asking the questions. I would now stop sharing. Okay, please go ahead. I will continue also to answer the questions that are coming in the chat. If you have any questions, please open your mic and camera to ask directly from our staff that are presenting here. For the rest of the matters, the meeting is officially concluded. I could read some of the questions that are in the chat that are not responded. In particular, okay, my colleague is responding them. So if you have questions that you ask in the chat, they will be responded as well. And thanks everyone for the kudos and thank yous. Thanks you for coming. Yeah. I'm going also to save the chat, and the questions that are in the chat, they will be shared also in text format. As David mentioned, you could also check out our material at the previous episodes of the same series on BubbleRAN.com/media/ORS series episode 02 and episode 01. Okay, if there are no questions directly asked, if there are no questions also in the chat, we would like to conclude the session now. You could send your questions, as I mentioned, to our email or be in touch on our social media. Thank you everyone for coming, and see you for the next episode of the webinar. Bye-bye.